Hello everyone, welcome to another lesson of physics. Today we are continuing on with our forces and going on to friction. So friction is a force that causes surfaces to stick together. So if you take a microscopic look at a surface, you're going to see that most surfaces are very bumpy and irregular, kind of like this brown background. So there are a couple ways to minimize friction. The first one is to smooth out a surface, so make it a little bit less bumpy. Another way is to lubricate it, so to have something a little bit more slick on top. All right, so we can see some examples. So if you zoom in really close on something like wood, you can see all these bumps and edges that'll give a lot of friction. Steel, you can see up close, is kind of bumpy as well. And on snow, you can see kind of structure that's here. All right, so when talking about friction, there's going to be something that we talk about called the coefficient of friction, which is shown by this Greek letter mu. And this is a measure of how much materials stick together. So this doesn't have any units, it's dimensionless. There are no units, meters, newtons, seconds, nothing like that. And what we'll see is the higher the coefficient, the more that these two surfaces will stick together. And the lower if surfaces are sliding past each other very easily. So let's take a look at some types of friction force. The first one that we're going to talk about is static friction. This occurs between two stationary objects, so neither one is moving. And we'll see that this keeps an object in place. The other type we'll talk about is kinetic friction, or also called sliding friction. Now this is going to occur between moving objects. And this is going to oppose motion, as in it acts in the opposite direction of its velocity. So we need to be able to find and use mu. So on our first page of our reference table, we're going to take a look right down here where our mu is, which is our coefficient of friction. So given a scenario where it says maybe rubber on concrete dry, we can find what its coefficient of friction is. So this is kind of a zoomed up picture where we can read each of them off. It gives us the kinetic and static frictions.
All right, let's take a look at each of these combinations below to figure out what their coefficients of friction will be. So we have a ski sliding on snow. So if we look up a wax ski on snow, and this is moving, so it's kinetic friction. So we'll find that it's mu, and we'll specifically call it mu k, is equal to 0.05. Then we have a hockey puck sliding on ice. So this will be rubber on ice, kinetic. To get mu k equals 0.15. Next, we have a wooden crate being pushed along a wood floor. So we take a look. Wood on wood being pushed. It's going to be kinetic, so 0.3 for its mu k. Next, we have a sneaker slipping up on a wet asphalt street. So it's going to be slipping, and a sneaker is rubber, and we got a wet asphalt street. So we're going to see that it is mu k equals 0.53. 0.53. Then we have a tire skidding in a dry concrete parking lot. So it's going to be rubber, concrete, dry. And it is skidding, so it'll be kinetic, so 0.68. So we'll get that mu k is equal to 0.68. So we'll see that the stickier the situation, the higher the coefficient of friction, or in other words, our mu.
Now we're going to calculate the friction force. So we'll see that the amount of friction is going to depend on the coefficient of friction, which we call mu. So we're going to have the static coefficient of friction, which we'll call mu s. This is the object is on top of the surface and motionless. And the kinetic coefficient of friction, which we'll call mu k. This is the object sliding across the surface. And this also depends on the normal force. So how hard something is pushing on it. So a greater normal force is going to result in a higher friction force. So from our reference table, we can get this formula that the force of friction is going to be equal to this coefficient of friction times the normal force. So Ff is the force of friction in newtons. Mu is the coefficient of friction with no units. And Fn is the normal force, also in newtons. So we'll see on both sides we end up with the units of newtons.
All right, so now let's take a look at an example of using our friction formula. So we have a wooden 15 kilogram block, and it's motionless on a wooden table. So now a force of 50 newtons is applied to the block. So we can say that's to the right. We have this applied force equal to 50 newtons. So now we want to find out what happens. So what we have to take a look at is if it's going to overcome the max static friction, so it overcomes this maximum static friction, which we can call FFS, it's going to be equal to mu s Fn. And this is our maximum static friction. If it overcomes this number, then it should start to move. So let's take a look. So we have this wooden block being motionless on a table, so it's wood on wood. So its coefficient of static friction, when we take a look at the reference table, is going to be 0.42 times the normal force, which it says is 147.15 newtons. So then from there, we can find out what our maximum static friction would be that we would have to overcome. This will be equal to 61.803 newtons. So in this case, the block is going to stay still. Right. So in addition, in this scenario, the actual force of friction on this is not going to be this 61.803. Otherwise, the friction itself would be pulling it, which never happens. So friction is never going to pull an object and speed it up. So when it's lower than the maximum and it's not moving, the force of friction is going to be equal to the applied force to keep it from moving. It's going to be 50 newtons. So now, what amount of force would need to be applied to overcome static friction? So as we said before, this is going to be 61.803 newtons. So now, let's take a look. So a force of 100 newtons is applied to the block. So then what is going to happen? So in this case, if we draw out our free body diagram, get the force of gravity down, its weight, the normal force keeping it up, this applied force, and the force of friction pulling back. So in this case, we're already given the gravitational force and the normal force. We're given that the applied force is 100 newtons. Now, the applied force is going to be greater than the amount we need to overcome of static friction. So let's see, that's going to start to move. Now, when it starts to move, the force of friction that's keeping it from moving is going to be our force of kinetic friction, which our force of kinetic friction is always going to be equal to mu k Fn. So the mu k is going to be a little bit different than the mu s. For wood on wood, it's going to be 0.3. It's going to be equal to this 147.15 newtons. So we get the force of kinetic friction. It's going to be equal to 44.1 newtons. So we can see it's less than this maximum static friction. So after it overcomes it, the friction kind of lays off a little bit. So we'll see from here, we'll get this net force if we subtract the two. That'll be equal to 55.9 newtons. And then from there, if we want to get our acceleration, we could do acceleration equals F net over m, plug in our values. So we got 55.9 newtons. And above, it mentioned that the block is 15 kilograms. So we can write in our 15 kilograms and get that this acceleration will be equal to 3.73 meters per second squared. So we'll see that it will start to accelerate due to these forces. Friction is going to decrease how much it speeds up, but isn't going to keep it from speeding up. All right, so now let's take a look at another example. So we have example number 2 right here. And we have a 60 kilogram skier sliding along a horizontal patch of snow with a constant velocity. So now what force must he supply to continue moving with a constant velocity? So here's a hint. We're going to follow this free body diagram process. So let's start off with our free body diagram. We will draw out each of our forces. So as always, we have this FG pointing down. We have a normal force pointing up, force of friction, slowing it down, and then we have to be applying some type of force. So that's going to be our free body diagram in this example. So let's draw our sum of forces equations. So we'll start off with our x direction. So we get that our Fx is going to be equal to the applied force in the positive direction minus the frictional force, because it's negative. And these are going to be equal to 0 because we want to maintain this constant velocity. So now we can write out our sum of forces equation in the y direction. So we got the normal force pointing up minus the gravitational force pointing down equal to 0. And those are our two sum of forces equations. So now let's solve each of them. So we want to know how much force needs to be supplied to continue moving with this direction. Now we'll find that we actually aren't getting any of the actual forces. All that we're given is that the mass is equal to 60 kilograms. But if we're given the mass, then we can find what the force of gravity is equal to, mg. So Fg equals 60 kilograms times 9.81 meters per second squared. So we get that 60 times 9.81 equals 588.6 newtons for our force of gravity. So now the next thing that we can find from our sum of forces equation is our normal force. It says that our normal force is equal to our gravitational force. So our normal force is going to be 588.6 newtons as well, because they balance each other out. So if we have this normal force, then we can try and find our force of friction. So our force of friction, we're moving with a constant velocity, so we have to have this mu k. It's going to be equal to mu k Fn. We can find our mu k on our reference table. So this is waxed ski on snow. So our kinetic friction is going to be 0.05 for our coefficient of friction. Then we say that the normal force is 588.6 newtons. It's equal to our force of friction. And we can solve this to find that the force of friction is going to be equal to 29.43 newtons. So now we said before that our applied force is going to have to equal our force of friction. So we get for our final answer that our applied force is equal to 29.43 newtons. All right, so that's it for today. That is friction. So you'll go through some examples and try some of these out on your own. All right, have a great rest of your day.